Okay, the next is angular acceleration.
Sir,
Yes.
sir, have you disabled the chat?
Just a second. Yes, it's able now. So the next is angular acceleration. So Sania, how many accelerations act in a non-uniform circular motion? The total number of accelerations in non-uniform circular motion?
3.
So one is centripetal, another one is angular, and the third one is tangential. So angular acceleration is just rate of change of angular velocity. Rate of change of angular velocity. So the rate of change of angular velocity is known as angular acceleration. We represent angular acceleration by alpha. This is rate of change of angular velocity. It's d omega over d. That's angular acceleration. It's a vector, axial vector. This is an axial vector. Its SI unit is radian per second square. That's angular acceleration. So after angular acceleration, there is one more quantity which is known as tangential acceleration. So Fazil, what is the cause of this tangential acceleration? Fazil, what is the cause of this tangential acceleration?
180.
Cause. Why this tangential acceleration comes into play? Yes, Abdullah. What's the cause of tangential acceleration?
The change in magnitude of linear velocity.
It is due to change in magnitude of linear velocity. This is the cause of tangential acceleration. You can write your tangential acceleration as dv over dt. Just the rate of change of linear velocity is tangential acceleration. Its direction is tangential to the circular path. Tangential to the circular path. This is the direction of tangential acceleration. That's tangential acceleration. Now, after tangential acceleration, and its unit is meter per second square. Meter per second square. Next, you can connect your angular and tangential acceleration relation between angular and tangential acceleration. So you know the relation between linear velocity and angular velocity. You can write your linear velocity v as omega into r. This is the relation between linear velocity and angular velocity. V is omega. So if I differentiate this quantity with respect to time, differentiating with respect to time, then it will give this is dv over dt, which is d over dt of omega. So this dv over dt is tangential acceleration. You can take this omega r as a constant and you are left with just d omega over dt. And what is d omega over dt? That's angular acceleration. So you get tangential acceleration is r alpha, or tangential acceleration is alpha. In vector form, you can write this as, in vector form, your tangential acceleration is the cross product of alpha and alpha. So these are the type of accelerations in a non-uniform circular motion. The first one is angular acceleration, which is equal to rate of change of angular velocity. The next is tangential, which is due to change in magnitude of linear velocity. And these two accelerations are related. Like tangential acceleration is angular acceleration multiplied by the radius of the path. Okay, just tell me one thing. This tangential and angular acceleration, are they independent or they depend upon each other? Tangential and angular, are these two accelerations independent or they depends upon each other? They depends upon each other, right? They are interconnected. AT and alpha are connected. So you can write that tangential and angular acceleration are dependent. They depends upon each other. So this tangential acceleration and angular acceleration depends upon each other. These two accelerations are not independent accelerations. So if I ask you how many independent accelerations are there in non-uniform circular motion? So what would be the answer? How many independent accelerations are there in non-uniform circular motion? Non-uniform circular motion have, yes, two independent accelerations. In total, there are three accelerations. One centripetal, tangential and angular. But tangential and angular are interrelated. So they are not independent. They are just two independent accelerations. One is centripetal, another is tangential. So these are two independent accelerations. The next is total acceleration in non-uniform circular motion. Total acceleration in non-uniform circular motion. So in non-uniform circular motion, we have in total two independent accelerations. So if a body is moving on a circular track, it will have two accelerations. One is acting towards the center, which is centripetal acceleration, and the another one is tangential. This is tangential acceleration. So the angle between them is 90. You just have to use parallelogram law to add these two accelerations. That's the net acceleration. It's centripetal and this is tangential. So the net acceleration is the sum of centripetal and tangential acceleration. So the net acceleration would be its root over its AC square plus AT square. That is the net acceleration. You can even calculate the direction. Let's say the net acceleration is making some angle alpha with the AT. This is the net acceleration. So you can calculate alpha using this right angle triangle. It's OAB. Each of the individual side represent a vector. So in triangle OAB, you can write your, okay, we are already using alpha here, so I won't take it as alpha. Let's take this as beta. Or let's take this angle as phi. So tan phi is perpendicular over base. Perpendicular is BA, base is OB. This BA represents this AC vector and OB represents AT vector. So this is tan phi. So tan phi is AC over A. This is tan phi. So this is how we calculate the angle between them. That's the net acceleration. So it is given that speed of the body is 10 meter per second. So your V is 10 meter per second. It's given data. The radius of the track is 2 meter. The tangential acceleration is 1 meter per second square. This is the tangential acceleration. Calculate the first part, centripetal acceleration. You need centripetal acceleration. So centripetal acceleration is simply V square over R. This is centripetal, V square over R. Your V is 10, so it's 10 square over R, that's 2. So that's 50 meter per second square. That is centripetal. Second one, angular velocity. So the relation between angular velocity and linear velocity is omega is V by R. It's 10 by R, R is 2, so omega is, it's 5 radian per second. Third one, the tangential acceleration 80. See, the tangential acceleration is rate of change of magnitude of velocity, which is given. Velocity change at the rate of 1 meter per second square. So your tangential acceleration is 1 meter per second square. In the fourth part, you need angular acceleration. We just have written that tangential acceleration is angular acceleration into radius of the path. So the angular acceleration is tangential acceleration divided by the radius of path. So the tangential acceleration is 1. The radius of the path is 2. So that's 2 radian per second square. Last one, fifth, total acceleration. So the total acceleration is sum of centripetal and tangential acceleration. So for total acceleration, always draw this circular path. Always draw the circular path. This is centripetal. This is tangential. Angle between them is 90 degrees. Very good, Apila. So this is the net acceleration. So the net acceleration is root over AC square plus A2 square. You can simply substitute their values. Like your AC is 50. AT is 1 square. So your A is 2500 plus 1. So it's root over 2501 meter per second square. Alpha. So this angle is alpha. So tan alpha is perpendicular upon base. Let's call this as beta. Tan beta is AC upon A. So this is the entire non-uniform circular motion. Is it clear, every part? So I can start with work energy in power. After work energy in power, we'll do laws of motion. So it will cover your school exams as well. I'm starting chapter number 6, which is work energy in power. Just after completing work energy in power, we will start laws of motion. Work energy in power. But before starting work energy in power, I need some portion of laws of motion. Some portion, few concepts of laws of motion. The first concept is that of Newton's second law. No, not Newton's second law. The first is the concept of momentum. So if you have a body of mass m, it's moving with a velocity v. So you can write that momentum of the body is the product of mass and velocity. So momentum is simply the product of mass and velocity of the body. Its SI unit is, if its SI unit is, it's kg meter per second. That is momentum. So if you have a body of mass m and it's moving with a velocity v, then its momentum is the product of mass and velocity. Its SI unit is kg meter per second. After momentum, the next term is Newton's second law. I will use all these topics in work energy and power. There's just 3 to 4 topics of laws of motion that we will use directly in work energy and power. That's Newton's second law. So Newton's second law simply says that if you have a body of mass m and you applied some force, F external force on the body, the external force acting on the body is just rate of change of momentum. That's it. The force acting on the body is rate of change of momentum. That you can even write this as mass into acceleration. It's rate of change of momentum, or you can even write this as mass into acceleration. That's Newton's second law. SI unit of force is Newton. CGS unit of force is dyne. 1 Newton is 10 raised to the power of 5 dyne. That's the relation between Newton and dyne. Third one. After Newton's second law, we have some particular type of forces, common forces in mechanics. Few common forces in mechanics. The first force is weight. Okay, this is very common. You must have heard about weight. So, when I will come to laws of motion, I'm doing this third topic, that common forces in mechanics, in very detail. When I'll come to laws of motion, that I won't, then I will not consider this particular topic called common forces in mechanics. We will do this topic in very detail in work energy part. Let's start with this thing, common forces in mechanics. Common forces in mechanics. This will take half an hour. I'm doing this topic in full detail, but when I will come to work energy and power, I will not, laws of motion, back to laws of motion, I will not take this topic. Common forces in mechanics. So the first force that we encounter in mechanics is weight. So what is weight? Weight is gravitational pull of Earth. Weight is gravitational pull of Earth. So the force with which Earth pulls a body is known as weight. Force with which Earth pulls is known as weight. That's weight. Or it always acts in downwards direction. It acts in downwards direction towards the center of Earth. So if you have Earth, this is Earth. I placed a body of mass m here, then the weight will act in downwards direction. When I say downwards, that means it's acting towards the center of Earth. If a body is here, then the Earth will pull this body towards its center. This would be the direction of weight. So weight will act towards the center. It always acts towards the center of the Earth. And we can calculate weight as mg. Weight is mg, mass into acceleration due to gravity. The product of mass and acceleration due to gravity is weight. After weight, so weight is the force which Earth applies on the body. So the force which Earth applies on the body is weight, which is m into g. Here g is acceleration due to gravity. The value of g is 9.8 meter per second square, which you can approximate as 10 meter per second square. So that is weight acting. After weight, the next force is normally action, or yes, normally action. So this is basically the force which two solid surfaces in contact exert on each other. So normally action is force which solid surfaces in contact exert on each other. So the force which the solid surface in contact exert on each other is known as force, as normally action. It acts perpendicular to the surface and towards the body. This is the normally action which is acting on the body. It acts perpendicular to the surface and towards the body. So if you have a surface here, so this is the surface here. And over the surface, I place this body of mass. This body of mass. So the force which is acting, now since this body and surfaces both are in contact, so the surface will exert a force known as normally action on the body. So normally action, how is normally action acting? Normally action is acting perpendicular to the surface and exactly towards the body. And the weight of the body is acting in downwards direction. Normally action always acts perpendicular to the surface. Instead of this body, if you have like two surfaces placed in this way. I place these two surfaces in contact in this way. Say normally action always acts perpendicular to the surface and towards the body. This is the normally action on body. Similarly, B will exert a normally action on A. So the normally action by B on A is N. And by Newton's third law, both the forces are equal and opposite. So A will exert a normally action NB on B to the right hand side, and B will exert a normally action on A, that is NA, to the left hand side, that's NA equal to A. After this, let's start with third type of force, which is friction. The third type of force is friction. Friction acting. So friction is an opposing force. This force opposes relative motion between two bodies. So friction, it opposes relative motion So if you have this surface, and over this surface, I placed a body or mass. If I try to move this body in this direction, and if this is a rough surface, then this rough surface will oppose the motion of this body. This will oppose the motion of this body. Friction always acts in a direction which is opposite to the motion of the body. This is the direction of friction. Friction always acts in opposite direction. This is the direction of friction. Friction tries to oppose the relative motion. Always oppose the relative motion. Say if you start a car, let's say you accelerate this car up to a speed of 100 km per hour, and then you switch your engine off. You're not putting brakes. You just switch the engine off. What will happen? The car will continue to move with 100 km per hour, or it will stop after some time. What will happen?
It will stop.
It will stop.
Sometime.
Stop after some time. Why would it stop?
Force.
Because of friction
Friction.
between the tires and road.
Yes, due to frictional force between tire and road, which is opposing the motion of the tire. So that is friction basically, which opposes the motion of a body. And the direction of friction is always opposite to the motion. Direction of friction is opposite to the motion of body. Friction always acts in a direction which is opposite to the motion of the body. So if a body is moving along x-axis, then motion will act in the opposite direction. Yes, Abdullah, if the surface is frictionless, then car will never stop. It will continue to move with 100 km per hour always. So that's friction. Now, how to calculate friction? The calculation is very simple. Friction is just coefficient of friction multiplied by normally action. This is known as coefficient of friction. And this n is normally action. Normally action. This coefficient of friction depends upon the nature of surface. If you keep on increasing the roughness of the surface, then this coefficient of friction will increase. This depends on the roughness of the surface. This coefficient of friction, it depends on the roughness of the surface, mu. And it's different for different surfaces. Like refractive indices is different for different medium. Just like refractive indices, coefficient of friction is different for different medium. Like for a smooth surface, its value is small. For a rough surface, its value keeps on increasing. That's coefficient of friction. Let's do few examples on friction. Say I take a surface and I placed a body of mass 5 kg. Fatma Farhana, how much is weight of this body?
Mass into gravitation.
The weight is mg. So it's 5g. How much is g?
9.8 meter per second
Or
square.
we can take this as 10.
10. Yes.
So that's 5 into 10. So how much is now?
50.
50, that's weight. Okay, Rania, what would be the direction of normally action acting on the body? Rania, it's always perpendicular to the surface and towards the body. Normally action will act in upwards direction. Okay, Sania, can you compare the value of n and this weight if body is not moving?
Yes, sir.
So, what is the relation between this n and weight of the body? If this body is not moving along y-axis, can you compare n and w? They should be equal or they can be different. They can have different values.
They are equal.
They are equal. If they have different values, then body will move. If upward force
Yeah.
then weight, then body will move. Body is not moving, that means n is equal to weight of body, which is mg. So your n is equal to 50. If I say that coefficient of friction is 0.3, so Fazil, what is the frictional force acting on the body? How much is the frictional force?
Mu into n, normal reaction force.
Yeah, so it's mu into n. So how much is mu? It's 0.3
into 50.
Reaction is 50. So how much is it?
15 Newton.
15 Newton. So the frictional force acting on the body is 15 Newton. A frictional force of 15 Newton is acting on the body. Let's do one more question, similar question on the same concept. I just want to make sure that everyone have understand this formula. Mass of the body is 10 kg. This is 10 kg. Calculate first normally action. Second, frictional force. Okay, solve it. Calculate normally action and then frictional force acting on the body.
So what is the coefficient of friction?
Yeah, coefficient of friction is, say, it's 0.2 here. This is weight and this is normally action. So normally action is 10g here. Yes, Fatma, you are correct. 10 into 10, which is 100 Newton. That's the first part. The second part, you can write your friction as mu into n. So mu is 0.2 into n, which is 100. So friction is, it's 20 Newton. Then the next is just one more force, that's tension. So tension is basically a force with which string pulls a body. So basically force with which string pulls. So if I take a box, I take this box, I connected this box to a wire, to a string. String means wire or rope or something. I applied a force F over the string. So I'm pulling the string. In turn, pulling this string is exerting some force over the mass, and that force is known as tension. So tension is the force with which string pulls a body. Like if I take this string. So this is a string. When I say string, it's rope, thread, wire, everything is string. I connected a mass through this string. Say I connected the mass through the string. If I pull the string, then this mass gets moved with the string. So the force which this string exert over the mass is known as tension. Like this one. This is the board. The string is pulling the board. The force which the string is applying to the board is known as tension. When I say string, string means rope, wire, thread, everything is string. And see, if you look at the direction of the tension is always away from the body. Direction of tension is along the string, away from the body. So this is the direction of tension. So tension always acts along the string and away from the body. This is tension. So if I put a body like this way, this is string, and this is string balanced a weight mass m. The tension in this string will act away from the body. Away from the body means upwards. So tension is simply the force through which string pulls the body. Force with which string pulls is known as tension. So the next thing is, there's one more thing. To start work, energy and power, I will use dot product. We did dot product in vectors. If I'm taking dot product of vector A and vector B, then the dot product of A and B is AB cos theta. This is how we calculate dot product in vectors. The next thing that I will use some basic trigonometry like cos 0 is plus 1. You should remember that cos 180 is minus 1. You should know that if theta is an acute angle, then your cos theta is positive. If your theta is an obtuse angle, then your cos theta will be negative. You should know one more thing from vectors, that if you have a vector A in this form, like it's A1 I cap, A2 j cap, and A3 k cap, and you have another B vector of the form B1 I cap, B2 j cap, B3 k cap. If I take the dot product now, like dot of A dot B, so dot of A dot B, simply you multiply the coefficient of I cap with I cap. You multiply A1 with B1, it's A1 B1. You multiply coefficient of J cap with J cap, it's A2 B2. You will multiply coefficient of K cap with K cap, which is A3 B3. So that's A dot B, it's A1 B1 plus A2 B2 plus A3 B3. Let's start work, energy and power. Work, energy and power starts with the concept of work done. So work done is the dot product of force and displacement. The dot product of force and displacement is known as work done. So let's say you have this surface. Over the surface, I placed a body of mass in. Body of some mass in. I applied a force F in this direction, and body displaced from here to here. this body gets displaced from here to here. Like it covers some displacement in this direction. It covers a displacement S in this direction. The angle between force and displacement is theta. So you can define your work done as the dot product of force acting on the body and the displacement of the body. This dot product of force acting on the body and displacement of body is known as work. If I open the dot product, then this will be Fs cos theta. This is the work. Next, this is the work. While using these two formulas, always remember these relations are valid if your force is constant. These relations are valid only for a constant force. You cannot use this relation for a variable force. This relation is valid for a constant force. If your force is constant, then only you can use this relation. You can't apply this relation for a variable force. Next, work done is a scalar quantity. Its SI unit is joule. Its CGS unit is erg. You can relate joule and erg that 1 joule is roughly 10 raised to the power 7. This is the relation between joule and erg. 1 joule is 10 raised to the power 7. And just one more thing. See, this work done of mechanics is not the work done that you studied in literature. Like in literature, even if you are sitting, you are doing some work done. You're sleeping, you are doing some work. But in mechanics, work done simply means you applied a force F on the body and body get displaced by some angle theta or some value S. Then the work done is this Fs cos theta. It's the product of force acting on the body, displacement of the body, and the angle between force and displacement. This product Fs cos theta is known as work. It's a scalar, SI unit joule, CGS unit erg, 1 joule is 10 raised power 7. This is the definition of work. After, let's take one simple example to calculate work done. Let's say your work done is Fs. Yes, now you are correct. Cos 60. Fatma Farhana, it's 10, it's 5, cos 60 is half. I guess cancel this thing. It comes out to be 25. So work done is 25 joules. So that's a simple problem. If your a constant force is acting on the body, then this is simply 25. Okay. Let's do one more example. This will use dot product. A force F equal to 2i cap plus 3j cap plus 5k cap Newton acts on a body. Due to this force, body displaced from point A, which is 3 to 1 meter, to point B, which is 1 meter. Calculate work. So this A and D, I'm giving you a hint. This coordinate of A and coordinate of B, this represents position vector of A. Position vector of A is 3i cap plus 2j cap plus k cap. And position vector of B is, it's 2I cap plus j cap plus k cap. The displacement from A to B is given by this relation. SAB is RB minus RA. That's displacement. Calculate work done. So RB minus RA. So first of all, we need displacement. Say work done is dot product of force and displacement. Work done is dot product of force and displacement. So you know your force. Your force is this. For displacement, you can use this fact that final position minus initial position is displacement. So you can write your displacement as RB minus RA. So your RB is 2I cap plus j cap plus k cap minus RA, which is 3I cap plus 2j cap plus k cap. So if I subtract them, your displacement from A to B comes out to be minus I cap, minus j cap and 0 k cap. So that is your displacement, minus I cap, minus j cap. So if I take dot product, force 2I cap plus 3j cap plus 5k cap. I can write this as a 0 k cap. Dot minus I cap minus j cap plus 0 k cap. Fatma Sharif, what is the coefficient of I cap here?
-2.
Minus 1, right? And here?
2.
So just multiply this 2 with minus 1. Similarly, the coefficient of j cap is 3. And here the coefficient of j cap is minus 1. So that's 3 into minus 1. The coefficient of k cap is 5 and k cap is 0. So 5. So the work done is, it's minus 2 minus 3. The work done is minus 5. This is the work done, minus 5. Okay, so let's erase it. So that was about the calculation of work done if your force is a constant force. This is for a constant force. If your force is variable, work done for a variable. Okay, let's do one more question for the constant force. Just one more question on the constant force. This is important. So instead of the flat plane, I just place this body on an inclined plane. This is it. This angle is, let's say, 30 degrees. I place this body here, body of 10 kg. There's a body of 10 kg. So, say the height of this plane is, say it's 10 meter. That's it. So you have to calculate work done, by gravitational force. Gravitational force means weight of body in carrying, weight is not carrying from A to B. So you're pushing this body from A to B. So you just have to calculate the work done by the weight in carrying this body from A to B. See, to calculate SAB, you can simply use this thing. Sine 30 is perpendicular upon base. So here perpendicular is 10 and your base is SAB. Sine 30 is half. It's 10 by SAB. So your SAB is 2 into 10. So SAB is 20 meter. Is it clear? Sania, Rania, and Fatih.
Yes, sir.
Okay, this SAB is 20 meter is correct to everyone. The next is I need work done. So your work done is Fs cos theta. Your force is weight, which is mg, which is 10 into 10, which is 100 Newton. Your displacement is 20 meter. How much is theta? Fatma Sharif, will you tell how much will be this angle between displacement and force? This much. How much is this angle, bache? Very simple calculation.
120.
120. Very good. This is 90 plus 30, so theta is 120. Very good. 120. Sorry, not meter. It's 120 degree. Now, if I calculate the work done, I put the values here. It's 100. Displacement is 20, and then this is cos 120. Cos 120 is minus half. If you don't know this value, you have to remember this thing. 120 is minus half. This is important. So this 2 will cancel this thing. Your work done comes out to be minus of 1000. This is how we calculate work done in case of an inclined plane. It's minus of 1000. Is it clear, everyone? We can solve this numerical using one more method, and that method is important. That's more common basically. There's one more method to solve this numerical, and that method is more common. The second method to solve this problem is through resolution of vector. Let's put this weight of 10 kg here. Weight is acting in this direction, which is 10g. Now, you can resolve this weight into two parts. You can break this weight into two parts. One is perpendicular to the inclined plane, and the another is along the inclined plane. You can resolve this weight into two parts. This we have recently done in resolution of vector in 2. This we have done last week in resolution of vector in 2. So if you have a vector, let's say this is x-axis and this is y-axis. See, if you forget this thing, if this is vector A and this angle is theta, then the component of A along x-axis is ax, which is a cos theta. Component of A along y-axis is ay, which is a sin. This is how we can resolve this vector A along x and y axis. Along x-axis, this is a cos theta. Along y-axis, the component is a sin theta. So the direction with respect to which you have angle theta, you get a cos theta component, and perpendicular to it, you get a sin theta component. And resolution means you are breaking a vector into two directions. Here we are breaking this vector A along two directions. One part is acting along x-axis, another part is acting along y-axis. Similarly, if this 10g is acting in downwards direction, this angle is theta, this is 90, this is 60, and this will be 30 degree. I need this angle, I don't need this 60 degree angle, so I'm just removing it. Is this 30 degree clear? If this is 30, then this would be 30.
Yes, sir.
Now, this 10g is making an angle 30 degree with this direction. So, along this direction, the component is 10g cos 30. And along the inclined plane, this is 10g sin 30. So, 10g is 10 into 10, sin 30 is half. So, it comes out to be 50. This is 10 into 10 cos 30 is root 3 by 2. That's 50 root 3. So we break this weight into two parts. One which is acting perpendicular to the inclined plane and another is acting along the inclined plane. We call this direction as perpendicular to inclined plane and this as along the inclined. So this is known as resolution that we have done in the last week. Okay, now just tell me, which component is responsible for the displacement of this 10 kg mass from A to B? This body is moving up the plane. So the force which is acting along the plane should be responsible for the motion. This 10g cos 30 is acting perpendicular. This will not contribute to the motion along the plane. This 10g cos 30 will contribute to the motion perpendicular to the plane. But this 10g sin 30 will contribute to the motion along the plane. So I call this as the x component of weight and I call this as the y component of the weight. I'm saying this is my x-axis, somewhat tilted x-axis and tilted y-axis. Okay, now tell me, is these resolutions are clear? They're solving the same question through one more method. This second method is important. Now we can calculate work. Let's calculate work done due to 10g cos 30. So Sania, what is the, say this is, I'm drawing it again. This is this. I'm moving from A to B. The displacement from A to B is SAB. And this is your 10g cos 30. Sania, what is the angle between SAB and 10g cos 30?
Thirty.
You see it again. This is SAB. From A to B, this direction is SAB and this is 10g cos 30.
90 degree.
90 degrees. So here your force is 10g cos 30. Your displacement is 20 meter that we calculated in the last part. Theta is 90 degrees. So if I calculate work done, this work done comes out to be is 10g cos 30 into displacement which is 20 into theta which is cos 90. Cos 90 is 0. So work done will be 0. So work done due to 10g sin 30. So the expression of work done is this, right? This is Fs cos theta. So force is this 10g sin 30. Yeah, this is your force 10g sin 30. So that's this we have calculated, which is 50. Then you have displacement. From A to B, the displacement is 20 meter. Now you need angle between these two forces. If I draw it here, this is the direction of 10g sin 30. It's acting down the plane. This is the displacement, which is up the plane. So what's the angle between displacement and force now? They are acting in opposite directions. If vectors are acting in opposite directions, that means angle between them is 180 degrees. Your angle is 180. So if I substitute all values here, your work done will be F, which is 50, S, which is 20, cos theta will be cos 180. So work done is 1000 Cos 180 is minus 1. So work done is minus of 1000. This is the work expression. So both the methods are identical. First and second method, you are getting the same result. The first one was easy. This is bit lengthy, but you should know this resolution. Without this resolution, you will stuck in questions of inclined plane. Do one more question on the same concept. This inclined plane is very important. We can't miss it. I'm just repeating the same type of question. This angle is 37 degrees. This is body of 20 kg. And this is given. This displacement is given as 20 meter. This is 20 meter, displacement of 20 meter. Calculate first part. Component of weight along and perpendicular to the inclined plane. Along and perpendicular to inclined plane. Second part. You need work done due to each component. In carrying body up the plane. So the mass is 20 kg. So its weight is 20 g. If this is 37, then this will be 37. In this direction, the component is 20 g cos 37. And along this direction, this is 20 g sin 37. So this 20 g cos 37 is 20 into 10. Cos 37 is 4 by 5. This is 2. This is 160. And this is 20 g sin 37. So it's 20 into 10. Sin 37 is 3 by 5. It's 4. It's 120. It's 120. So that's 160 Newton and this is 120. That's it. These are the components of forces. If we calculate the work done, due to 160 Newton, then work done is Fs cos theta. Work done is force, which is 160, displacement, which is 20, and this one, this angle is 90 degrees, cos 90. Cos 90 is 0, so work done is 0. If I calculate work due to this 120 Newton force, then this is work done is Fs cos theta. Your force is 120, displacement is 20, cos theta. So force is acting in downwards direction and displacement is upwards. It's cos 180. So work done is 120 into 20 cos 180 is minus 1. So it's minus of 2400 joule. That's the answer. So that was about work done for a constant force. If a constant force is acting on the body, then you can have these type of numericals to calculate work done. These three type of questions are very common.